In this video, we will examine different assumptions that lead to different asymptotic variance calculations for Poisson regression. Recall that we defined the score vector as the partial derivative of the log likelihood with respect to beta, and for the Poisson regression model, we showed that it took the following form. It's also useful to have a name for the second derivative matrix of the log likelihood with respect to beta. We're going to call this the Hessian matrix. We'll use that name, and we'll use the notation H throughout these lectures. This is defined as the derivative of the score vector with respect to beta prime. And for the Poisson regression model, we see that the Hessian matrix takes the form negative e to the x prime beta times the outer product of x prime. Using this notation, we can express the matrices J and K from our theorem for potentially misspecified conditional likelihood estimation as follows. J is equal to minus the expected value of the Hessian evaluated at beta naught, which is the true parameter value, while K is the variance of the score vector evaluated at beta naught. And because we know that the score vector will be 0 at the population analog of the maximum likelihood estimator, namely at the pseudo-true parameter value, this variance doesn't actually have to have the second term in it. We know that a variance is equal to the expected value of the outer product of a vector minus the outer product of the expectation, but the second term will simply be 0 by the first order condition. So this K matrix is the same thing as the expectation of the outer product of the score evaluated at the pseudo-true parameter value. And substituting the expressions above for Poisson regression, we obtain the following expressions for J and K in this model. Notice that while J does not depend on the outcome variable y, K does. To see how this works, let's recopy the expression for K in Poisson regression from the previous slide. Namely, K is equal to the expected value of this residual evaluated at beta naught squared times the outer product of x prime. Using iterated expectations, we can write this as the expected value of u squared given x multiplied by x prime, since we can pull the x prime outside of the inner expectation given that it's a constant conditional on x. Now substituting the definition of this ui, we obtain the following expression. But notice, now that we've written it in a different way, that this inner conditional expectation is simply the conditional variance of y given x. In other words, the conditional variance of y given x is defined as the expectation of y minus the conditional expectation of y given x, quantity squared, conditional on x. That was a mouthful, but it's what I've underlined here. So what this shows us, given that J does not depend on y but K does, is that different assumptions we might care to impose about the conditional variance of y given x will affect the asymptotic variance of the Poisson regression estimator through their effect on K. We will consider three possible assumptions for the variance of y given x, and I've ordered them here from the strongest assumption to the weakest assumption. The first and strongest assumption is called the Poisson variance assumption. This is the assumption that the variance of y given x is equal to the expectation of y given x, which holds if the Poisson model is correct, which we can see from looking at the calculations for a Poisson distribution from our first lecture, where we talked about the fact that the mean and variance of a Poisson distribution coincide. So that's the strongest possible assumption, and it would hold if the Poisson model is correct. A weaker assumption, which is much more plausible in practice, is called the quasi-Poisson assumption. This assumption says that the conditional variance of y given x is equal to a scalar multiple of the conditional mean of y given x. This allows for the possibility that y given x does not follow a Poisson distribution. When this constant sigma squared is greater than 1, a situation that we call over-dispersion, the conditional variance of y given x exceeds the conditional mean of y given x. When sigma squared is less than 1, a situation that we call under-dispersion, the conditional variance of y given x is less than the conditional mean of y given x. And if we're in the unusual situation that sigma squared is exactly equal to 1, then we're just back to the Poisson assumption. So we see that this quasi-Poisson assumption is strictly weaker than the Poisson assumption. The weakest possible assumption that we can make is no assumption at all. So we'll also consider what happens if we leave the variance of y given x totally unspecified. We'll start off by taking a closer look at the Poisson variance assumption to see what happens to the asymptotic variance of the Poisson maximum likelihood estimator under this assumption. I've recopied the expressions for j and k at the top of the slide. So substituting in variance of y given x is equal to expectation of y given x, which we have assumed throughout this lecture takes the form e to the x prime beta naught. This tells us that k is equal to the expected value of e to the x prime beta naught times x prime. Hence, under the Poisson variance assumption, k equals j, which is the information matrix equality we saw in Lecture 1. Therefore, under this assumption, the Poisson regression estimator is asymptotically normal with mean vector 0 and variance covariance matrix J inverse. A sample analog estimator of J inverse is the following quantity, which simply replaces the population expectation with a sample average and the unknown true parameter value beta naught. And I said true here because this Poisson variance assumption holds when, in fact, the Poisson assumption is correct, with the maximum likelihood estimator beta hat. And we can show, although I won't do it here, that this estimator j hat inverse is indeed consistent for j. And it doesn't matter if the Poisson assumption is correct. In fact, this estimator of j is consistent regardless. It's just a sample analog estimator where we've substituted in a consistent estimator of beta naught. The only thing that changes, depending upon whether we're thinking about our model as correctly specified or not, is actually the interpretation of beta naught, and indeed what the form of the asymptotic variance matrix will be. So under this Poisson variance assumption, the asymptotic variance matrix is simply J inverse. Now let's explore the consequences of a weaker assumption, namely the quasi-Poisson variance assumption. Here we will assume that the variance of y given x is equal to sigma squared times the expectation of y given x, and we have assumed throughout this lecture that that conditional expectation equals e to the x prime beta naught. Substituting into our expression for k at the top of the slide, this implies that k is equal to sigma squared j, and therefore substituting into our key theorem for conditional maximum likelihood estimation, we find that the asymptotic variance matrix J inverse K J inverse that obtains when we do not assume that the model is correctly specified simplifies to sigma squared J inverse. So this quasi-Poisson assumption allows the Poisson assumption to be wrong, so we don't necessarily assume that the distribution of y given x is Poisson. However, it does nevertheless give us a simplification of J inverse K J inverse. That's because it's not fully general. It does impose some structure on the conditional variance of y given x. Under this assumption, we obtain the following asymptotic distribution for the conditional maximum likelihood estimator b hat, namely that it is asymptotically normal with mean vector 0 and variance covariance matrix sigma squared J inverse. The consistent estimator of J hat inverse from the previous slide is still consistent here, as I described a moment ago. The consistency of that estimator didn't have anything to do with whether the model was correctly specified. So the remaining question is, how could we estimate this scaling factor, sigma squared, that allows there to be a difference between the conditional mean and conditional variance? To find an estimator for sigma squared, we will go through some simple derivations using iterated expectations. Under the quasi-Poisson assumption, the variance of y given x is assumed to be equal to sigma squared times the expected value of y given x. Rearranging to solve for sigma squared, we obtain sigma squared equals the conditional variance of y given x divided by the conditional mean. Now, by definition, the conditional variance is equal to the following expression. But notice that the conditional variance is a conditional expectation of something given x. And this expectation of y given x in the denominator is just a function of x. So we can view this object as 1 over y given x, 1 over the expectation of y given x, I should say, as just some function of x. Thus, it can be pulled inside of the conditional expectation to the left, yielding the following expression. Now, substituting our assumed form for the conditional mean function of y given x, e to the x prime beta naught, we obtain the following expression. And now we find ourselves in an interesting situation. We would like to use iterated expectations, but how can we do that? Well, sigma squared is a constant. And the expectation of a constant is simply equal to that constant. So we can take the expectation of both sides of the expression, confident in the knowledge that that will not change the left-hand side. It's a clever trick in this particular instance. So let's do that. Taking the expectation of the expectation given x of this complicated expression, by iterated expectations, we find that the result is sigma squared is equal to the expectation of the ratio of y minus e to the x prime beta naught squared over e to the x prime beta. And by the definition of the residual u from earlier in this video, we find that sigma squared is equal to the expected value of u squared over e to the x prime beta naught. Now, this expression is a bit more helpful for thinking about how to estimate sigma squared. It immediately suggests that we should have a look at the residuals from Poisson regression. And indeed, replacing the expectation with the sample analog and these population residuals u squared of beta naught with these sample residuals, we do obtain a consistent estimator of sigma squared. Just to be clear, I haven't proved that this estimator is consistent, but one can do so. I've merely suggested it based on the analog estimation principle. I showed you a population object, and I suggested replacing a population mean with a sample mean, and replacing an unknown population parameter beta naught with an estimated sample parameter beta hat. The weakest possible assumption that we can make about the conditional variance of y given x is to make no assumption at all. This gives rise to the robust asymptotic variance matrix estimator for Poisson regression. There's really nothing new to add here, except that, in this instance, we have to estimate k. It turns out that the following is a consistent estimator, although we will not prove it. And this should look relatively familiar to you. This is almost exactly the same way that we estimate a robust asymptotic variance-covariance matrix for ordinary least squares. So we are simply substituting the sample residuals here for the population versions, u of beta naught, and we're doing that by substituting our maximum likelihood estimator beta hat for the pseudo-true parameter value beta naught. So if we want to think about these three possible assumptions that we could make, the robust asymptotic variance matrix on this slide, which has us estimate j, k, and j to construct an estimator j hat inverse, k hat inverse, j hat inverse, this sandwich form of an asymptotic variance-covariance matrix, this is the safest assumption. It does not place any restriction on the conditional variance of y given x, and as the sample size goes to infinity, we will obtain a consistent estimator of the asymptotic variance-covariance matrix, no matter what the true data-generating process might have been. It doesn't matter if the Poisson assumption holds. It doesn't matter if the quasi-Poisson assumption holds. Anything goes. It's still going to work. The downside, of course, is that when we make fewer assumptions, we are typically going to be left with somewhat more badly behaved objects. And indeed, this product of j hat inverse, k hat, j hat inverse can be rather noisy in small samples. So it's somewhat more common in count data applications to actually work with the quasi-Poisson assumption, which is not as general as the assumption on this slide, because this slide doesn't use any assumption at all on the variance of y given x, but does allow for violations of that extremely restrictive Poisson assumption that said that the conditional variance equaled the conditional mean, while nevertheless giving us a much simpler asymptotic variance-covariance matrix to estimate. Because remember, in the quasi-Poisson case, all we needed to do was get an estimator of sigma squared, that's a scalar, and then an estimator of j. Whereas here, for the robust asymptotic variance matrix, we need to estimate these two matrices, j and k. Towards the beginning of this lecture, I mentioned that you could have chosen to use nonlinear least squares rather than Poisson regression, but there was a reason why in practice Poisson regression is more commonly used. Very briefly, to finish up the lecture, I'll tell you a bit more about this. Throughout the lecture, we have maintained that the conditional mean of y given x is equal to e to the x prime beta naught. That wasn't really necessary. What was necessary was that we specify some parametric form m of x in terms of beta, such that m is strictly positive. This just happens to be the most common choice in practice. The thing that's important is that we were willing to specify a parametric form for this conditional mean function. If we're willing to make such an assumption, it turns out that we can show that both Poisson regression and nonlinear least squares are consistent for beta naught, provided that we have indeed specified this conditional mean model correctly. So how can we choose between nonlinear least squares and Poisson regression? Well, it turns out that count data are typically heteroscedastic. We can see this in the Poisson model. So under the Poisson assumption, the variance of y given x is equal to the expectation of y given x. So that definitely varies with x. But even without the Poisson assumption, it tends to be the case that count data are extremely heteroscedastic. And in a heteroscedastic world, it turns out that nonlinear least squares is relatively inefficient. What this means is that it has a relatively high asymptotic variance. So we're actually able to formalize this, and on this slide I'm just going to summarize two key results. There are other sorts of results one could prove in this setting to try to compare the efficiency of Poisson regression to that of nonlinear least squares, but here are two simple results. So the first, if the Poisson model is correct, then of course it turns out that Poisson regression is the best thing you can do. It has the lowest variance among all estimators that leave the distribution of x unspecified. In other words, the lowest variance among all estimators that are conditional likelihood estimators. However, it turns out that even without this assumption, so under the weaker quasi-Poisson assumption, which I mentioned before is fairly common in practice and might be considered to be a relatively good approximation for many kinds of count data, Poisson regression can be shown to be more efficient than nonlinear least squares. So the idea here might be, if we're working with count data and we think something like the quasi-Poisson assumption is reasonable, there's a good reason to choose Poisson regression because it's going to result in estimates of the same parameter, beta naught, that have a lower asymptotic variance.